All right, everybody, I want to point out that the ride board that was emailed out to you has had people offer rides. And so if you need a way to get to the airport, go look at the ride board. We're going to be resuming the second half of the Piecing the Puzzle Together session. The second talk is a student and our final student, so be ready the moment that talk is done to enter your scores. So for our first talk, we have Ryan Venturelli talking about what lies beneath, using sub-ice archives to assess the Holocene instability of the West Antarctic ice sheet.
Thank you. Oh, I'm really small. Hello. My name is Ryan Venturelli. I'm a postdoc at Tulane University. Before I get started telling you about what lies beneath, I'd like to thank the organizers of the WAIS Workshop Committee for a great meeting so far and also giving me the opportunity to talk to you all today. So, drilling holes through ice takes a whole lot of people to accomplish these things. So, even though I'm the person up here talking to you today, this is work that I've done in collaboration with my supervisors, Brad Rosenheim and Brent Gehring, as well as the SALSA science team and ITGC GHC team, who have worked really hard to drill holes through the West Antarctic ice sheet to collect soft sediments and bedrock from beneath grounded ice. As you probably guessed from my question earlier, I'm a paleo person, and I'm really interested in how we can kind of link these paleo observations with the processes that we observe today. And one of the big things that we really need when we're looking into the past is something that we can tie a chronological constraint to. So, datable material that records ice sheet change. And this image here on my slide shows all of the existing published marine data that tell us when and how ice retreated from the continental shelf to its present position, constrained by marine radiocarbon. And the points on land tell us about the exposure history of Antarctic ice, so when ice left these areas. But one of the things that you'll notice in this map is that all of the points are from ice-free areas. And that only allows us the opportunity to ask questions of when did ice leave this area? And in order for these paleo processes to really be incorporated in models, as we heard from Ted earlier during the discussion, we need to start to understand the processes at play. And one way that we can do this in the paleo record is looking under the ice. And instead of asking, how did ice get to where it is today? Was West Antarctic ice less extensive in the recent past, the Holocene, than it is today? So, some ways that I have started doing this is measuring radiocarbon in samples from subglacial lakes and the sub-ice shelf environment. Radiocarbon in this context is found in organic material in sediments underneath the ice, and provides a way that we can measure the timing that the ocean was last in this area. But like I said earlier, we need something datable, and the only thing there that we have is this kind of really weird mixed up mud that has some material that's really old and some material that does have radiocarbon in it. So just simply measuring a sample of this mud won't give us an age that aligns with deposition or aligns with when the ocean was last in this area. In fact, in the subglacial environment, there's so much old material that this measurement will be biased towards the old. So in order to use this material that we recover from the subglacial environment to tell us something about when it was deposited, we need to find a way to break apart that mixture. And the way that I have done that so far is applying a method called ramped pyrolysis or ramped pyrox. This method exposes a sediment sample to a constant temperature ramp that exploits basically the difference in thermochemical stability between that really old stuff that's been hanging out for a while and the stuff that was more recently deposited in the Holocene. And this allows us to use kind of the low temperature end of this spectrum to gain a really nice chronological constraint of when the ocean last touched the subglacial environment. And you'll see that when I show you the data from this method, we can really start to answer a lot more questions about when these muds were deposited. So this graph that I have up here is kind of a lot to handle unless you're constantly living in isotope space like I am. So I've broken it down a little bit. A bulk measurement is something that hasn't been broken apart, so those are the blue points. On the x-axis, I have the stable carbon isotopic composition that gives us an idea of the environmental context that this carbon was deposited. And on the y-axis, I have radiocarbon, and this gives us a connection to time. And you'll see that I've drawn this silly little line with arrows on it through the data. And when we start to see a linear relationship existing in isotopic systems, it can give us insight into basically how these two end members, how the new material and the old material are mixing, and allow us to figure out how much new material is there and how it got there in the first place. So these two end members that I'll talk about today on the old side have been deposited over a long period of time when West Antarctica was much smaller than today, and we had open seas over West Antarctica. And we see that in the stable isotope values that indicate open marine kind of productivity. When we move to this new end member on the top corner of the arrow, we start to learn that the ocean touched Antarctica more recently than we have traditionally thought by looking at these ice-free archives. In fact, as recent as the Holocene. And the really depleted signature in stable carbon isotope space tells us that this deposition didn't happen in an open marine environment. It happened beneath the cover of an ice shelf, and in fact probably got there by assimilation of the existing microbial biomass that lives in the subglacial environment. So now we can start to use these geologic archives to reach out to collaborators that think about why these microbes are here and how there are existing communities beneath the ice sheet, as well as kind of when the ice sheet changed and why that matters to kind of the future. So this method has helped us to determine that the Sipal coast of West Antarctica retreated sometime about 6,000 years ago with a 2 sigma error bar of about 1,000 years. Using both the actual measurements of the sub-ice shelf sediment that I described in detail earlier, but also a Monte Carlo simulation through the very sparse paleo data that we are able to generate with these efforts. And then looking into areas where we don't have sediment, but instead have subglacial bedrock, we can start to think about radiocarbon in a different way. And instead of radiocarbon being brought in by things that live in this environment, we have radiocarbon that accumulates in rocks as they're exposed at the surface. So some of the work that I'm part of is part of the Thwaites Glacier collaboration, is shifting my focus not from the Sipal Coast region to the Thwaites Glacier region, and looking at whether or not Thwaites and Pine Island glaciers were smaller than present in the Holocene. So there is a lot of existing data in this region that tells us that ice thinned to its current position between 6,000 and 3,000 years ago, but there's kind of this gap of what happened after that. And we're trying to figure out basically if ice thinned and re-advanced. This is work that's currently in progress, so here on this slide I have just kind of what we expect to find. So if the bedrock that we drilled into was exposed sometime in the Holocene since the ice surface got to where it is today, we would expect to see an accumulation of in situ carbon in the top of our subglacial bedrock cores, as you see in this blue curve here. And if we don't see anything, then we'll just kind of have the straight up line that is shown with our null hypothesis of no radiocarbon in the rocks. So as we start to think about how we plan to fit these puzzle pieces together of this session and the session before this, I think one really important element that is underutilized so far just because of inaccessibility and lack of opportunity is these subglacial archives. And I would be really interested in hearing from you in the discussion of how we can drill some more holes through West Antarctica and collect more sediments and bedrock to really explore whether or not West Antarctica was smaller than present in the Holocene and why. So, thanks.
Wonderful. Next, we have Louise Borthwick, who is a student, so get your judgmental devices ready. She's going to be talking about tectonic influence on bed character variability under Thwaites Glacier, West Antarctica.
Hi, hello. Yes, I'm Louise, and I'm a PhD student at Temple University working with ATSU. And we also have collaborators on this project from Columbia and Penn State as well. So yes, today I'm going to be talking about tectonic influence on bed character variability under Thwaites. So Thwaites is located here in this red box, and as we just heard in the last session, it's a very important part of the West Antarctic system. And today I'm going to specifically looking at the upper crustal structures under Thwaites and how they relate to the conditions at the bed of Thwaites. So the bed of Thwaites has a number of bedrock ridges and troughs, and we can see one of these ridges on the left and troughs on the right over this 38-kilometer profile. And what this profile is showing is the type of bed found at the base of the glacier from acoustic impedance measurements. So the bed can be classified in two ways. We've got soft bed, which is when the material underneath the ice does deform. So that's typically when we have a layer of sediment between the ice and the basement rock. And then we have hard bed, where the material underneath the ice does not deform, so that's typically where the basement rock is exposed. And what we can see is in this depression on the right here, we have fairly continuous soft bed, whereas we move to the more undulating area to the left, we have hard bed on the Stutz side of bumps and soft bed on the lee side of bumps. And this pattern of bed type and topography was also found at a second location further downstream. And the exact placement of these hard and soft bed types on the bedrock ridges and troughs of Thwaites has been shown to influence the eventual rate of retreat. So it's important to know if this relationship between bed type and topography is seen over the whole glacier and at more than these two locations of the seismic surveys. And to do that, we need to look at how the distribution of bed type and topography formed. So there's multiple other fast-flowing ice streams and glaciers in West Antarctica which flow within basins which are formed by rifting, probably by extension from the West Antarctic Rift System. So the West Antarctic Rift System roughly influences the area between the two dashed red lines. And the Saipo Coast and Foligno ice streams and Pine Island Glacier have all been shown to have their fast flow contained to the area of continuous soft bed where a rift-formed basin has filled with sediment. As I just showed, Thwaites instead seems to flow over areas of continuous soft bed and areas of mixed bed type. So we are hypothesizing that the area of continuous soft bed is actually the top of a rift-formed basin, and therefore that Thwaites is flowing over these rift-formed basins rather than being confined by them. So to investigate these upper crustal structures on Thwaites, we're using a multimodal geophysical method to reduce the non-uniqueness in each of the individual methods. So we have long offset seismic reflection/refraction over this 42-kilometer section, and that data was collected in 2008-2009 field season, and that's actually the location of the seismic acoustic impedance measurements that I showed you in the second slide. So we already know the distribution of bed types in that location. And then we've extended the model to a full 225 kilometers using airborne gravity and magnetic data. So firstly, to look at the seismic data, and from examining the seismogram, we found reflections from the bottom of a half-graben-shaped sedimentary basin. So the dots are showing the modeled reflections from the bottom of the sedimentary basin, and the open circles are the reflections I've picked in the seismogram. So you see the P-wave reflection and multiple other converted reflections from the bottom of this half-graben basin. And then also from examining the seismogram, we found there to be no head wave arrival in the seismogram. So a head wave will typically travel along the layer where there's a higher velocity rock below, and we would expect to see it overtake the P-wave arrival from the bottom of the ice, as we can see from these green dots overtaking the blue dots. But as we don't see this in the seismogram, we therefore have included a sedimentary rock layer in the model, which has a lower velocity than that of the ice. So combining the half-graben-shaped sedimentary basin and the sedimentary rock layer over the 38-kilometer section of the seismic data, we've got the half-graben-shaped sedimentary basin underneath the continuous soft bed, and then the sedimentary rock layer underneath the ice. And when we extend that to the full 225-kilometer model length, using the airborne gravity and magnetic data, we've placed more half-graben-shaped sedimentary basins under all the areas which were more bedrock depression areas where we would therefore expect to see the soft bed. And what we can see in the gravity data is that over each of those sedimentary basins is a low in the gravity data. So the open blue circles are showing the gravity measurements, and the red line is my model, the gravity calculated from my model, which is a sum of contributions from the topography, the sedimentary basins, the sedimentary rock, and varying moho depth. So the fit isn't completely great at the moment, but we're going to improve it by varying the density of the layers in the model and the depth of the sedimentary basins, and then also looking at the topography either side of this 2D line to take into account 3D effects as well. And the magnetic data, we're using magnetic depth to source measurements. So that measures the depth to the magnetic source in the crust. And typically sediments will have very low magnetic susceptibility. So we'd be expecting the depth to source solutions to lie outside of the sedimentary basins. And we can see clustering of these depth to source solutions around the edges of the sedimentary basins, showing agreement with the model created from the gravity data. So far on this one line on Thwaites, we've found evidence for half-graben-shaped sedimentary basins from multiple geophysical methods, and evidence for sedimentary rock layer in the seismic data. And the geometry of these upper crustal structures indicates a tectonic influence in their formation, and therefore a tectonic influence in the distribution of hard and soft bed types over Thwaites. To investigate if this tectonic influence is seen over more than just this one line, we're planning a further long offset seismic reflection/refraction survey further downstream, and that's as part of the ITGC Thwaites GHOST project. And then we're also planning to use the airborne gravity and magnetic data that already exists over much of Thwaites. But so far, this is an initial indication that tectonics are influencing bed character variability over Thwaites. And I'd like to acknowledge these people for collecting my data and providing the money for this survey study, and my contact details there.
Great talk. Everyone enter your scores right now. All right. Next, we have a virtual talk from Jamey Stutz, resolving solid earth properties through co-location of high-resolution ice load histories and GNSS measurements in West Antarctica.
Kia ora, everyone. My name is Jamey Stutz, and I'm a postdoctoral researcher at the Antarctic Research Center here at Te Haranga Waka, Victoria University, Wellington. I'm a long-time listener and first-time caller, so I'd like to start off thanking the WAIS Workshop organizers for their hard work putting together such a fantastic lineup and for the opportunity to present today. I'd also like to acknowledge the collaborators on this project. We have an ambitious aim to integrate the understanding of glacial isostatic adjustment and glacial geology. So just really thankful for the supportive colleagues on this project. To start, I'd just like to draw your attention to this map made by Whitehouse et al. To highlight the existing network of PolNet GPS stations and geological records of past ice load. At this scale, we can see quite a few areas with coverage by both GPS measurements and ice load records, but vast regions with sparse data control from one or the other. In this talk, we aim to highlight the effort to obtain records of past ice load at PolNet sites by PolNet field team to further understand the solid earth properties needed for GIA modeling. We'll do this by featuring 2 sites that serve as a proof of concept and provide motivation for future work. So the main tools that I use to reconstruct the ice load histories are cosmogenic isotopes, which are, when extracted from glacial deposits or bedrock, allow us to determine the surface exposure age, that is, the time since a rock was dropped off by a thinning ice sheet. Essentially, exploding supernovae produce high-energy particles that interact with the upper atmosphere and the surface of the Earth to produce cosmogenic isotopes in the crystal lattice of the rocks. And drastically oversimplifying here, if we can count up those cosmogenic isotopes and with a better knowledge of how fast they're produced, we can back out an exposure age. And if we take this a step further, let's have a look at how we produce an ice history to reconstruct the spatial footprint and thickness of the ice sheet through time. If we take a cross-section through this cartoon glacier, we can see that there are entrained glacial erratics, and as the ice thins and deposits its higher elevation erratic, the cosmic clock starts, and we have our first point on the plot of thickness with time. As this simple case proceeds, we pick up a few more points and are able to derive an ice load history at this site. So if we extend this method over multiple sites, we can further constrain the ice load footprint. And it's really worth mentioning here that it's quite an oversimplification. This method does not help with times of thinner than present ice and is sometimes complicated by local cold-based ice cover. Ultimately, this ice load constitutes the load on the Earth that produces glacial isostatic adjustment, which represents the solid Earth deformation due to past ice mass change. And importantly, for us, this method allows us to reconstruct the ice load history on centennial to millennial timescales. So jumping into the modern day, as I mentioned, PolNet has installed a network of GPS sites around Antarctica that measures the total uplift at a particular site, and this is an integrated signal. So one component of that total displacement is due to the elastic response due to more modern ice mass changes, and the other is a GIA, or viscoelastic response, from longer-term ice mass changes. So a way to determine the elastic component is to use a modern ice history together with an elastic Earth model supported by seismology, which is also co-located at PolNet sites. So here we can see the total vertical displacement from the PolNet network. The sites around the Amundsen Sea and Bayman are clearly winning the fastest uplift prize, but we need to subtract the elastic response due to modern ice mass changes. And Durkin et al. Have done this in a really clever way using satellite altimetry to reconstruct changes in ice mass through time, essentially a decadal record. And in this way, they use the elastic Earth properties to model the response to this modern mass change. So removing this elastic component, the residual component of deformation is the viscoelastic response due to longer-term ice mass change on the order of centennial to millennial timescales. Ultimately, this is what's used for GIA modeling constraints. So it's worth highlighting here that GIA modeling is really important to determine modern ice sheet mass changes and to constrain Earth properties, primarily mantle viscosity, which is the major control on rate and deformation response. An example of this comes from Barletta et al., where they derive the mantle viscosity by GIA modeling, constrained by measured crustal displacement from GPS. Here they needed a well-constrained ice history model to derive a robust Earth model. They used an ice history scenario that was constrained by altimetry and then extrapolated back in time due to a lack of data constraints over this time period. So this study infers a centennial timescale of ice mass loss that yields a super low and squishy mantle viscosity in the 10 to the 18th Pascal second range. So ultimately, if we have an accurate ice history, then we can use a GPS measured and elastic corrected deformation to find the kind of best fit Earth properties. So how do we improve our ice histories in order to improve our GIA models? I propose we collect rocks. It's worth mentioning here that there are a lot of researchers working on this in the field, in the lab, and we highlight the utility of determining ice load histories at GPS sites to contribute to the more detailed ice load reconstructions. An example of this can be found in the Marie Birdland. Basically, this seminal study of Stone et al. Constrained the mid-Holocene thinning of the Boyd Glacier and really opened the floodgates to this, what we call the dipstick method. Basically collecting glacial erratics along vertical transects at multiple sites demonstrated the utility of this method to reconstruct past changes in ice mass. Flash forward a decade, and during the maintenance visit to the GPS site here at Clark Mountains, Terry found a few attractive glacial erratics and striated bedrock to boot. Exposure ages from these samples show a late Holocene age that correlates well with the existing reconstruction. So the Terry's points here in green and the existing reconstruction in red. So really this provides us, and just another plot here showing them in a combined elevation above modern ice surface with exposure age, showing that kind of rapid signal around 3,000 years ago. So this provides us confidence that we can collect meaningful data while also performing critical updates to the GPS network. So pretty exciting. And so another exciting example that provides a proof of concept for us, YZ Lepley Nunatak in the Bellingshausen Sea sector. So here the ice history is essentially unconstrained. The helpful reconstruction from the RAISed consortium is dominated by onshore and offshore data in the Amundsen Sea sector, as well as a few sparse data in the offshore as you get over to the peninsula. So, Lepley really serves as one of the few dipsticks out here in this area while, kind of providing this really great opportunity. And Terry had another great sampling campaign visiting this site where she collected a few glacial erratics. This should connect really well with the more detailed glacial geology studies in the Jones Mountains that's emerging. So it's with a teeny bit of disappointment that the only results I can provide is this nice image of precipitated beryllium gel overlooking the Wellington Harbor here from our cosmogenic isotopes lab here in Wellington. These samples are currently in the AMS facility in Sydney, and Klaus should have these results for us any day. So it's also worth highlighting that other emerging case studies are on. As part of New Zealand's Antarctic Science Platform, our glacial geology group has targeted a few other PolNet sites for further constraints on the ice load histories. So in 2019-20 field season, we collected a few glacial erratics from the southern Transantarctic Mountains. This one at the one at the lower Skelton Glacier, Fishdale Point GPS station, as well as another on the upper Bird Glacier at Lone Wolf Nunatax. And we've got future focus on field season planned along the eastern Ross ice shelf at the Rockefeller Mountain. So we'll look forward to progressing with this project in this way. Also, it's even, with this incredible co-located network of GPS measurements and emerging constraints on ice load histories, there's still massive gaps, spatial gaps in this kind of co-located network. So we're looking out for future opportunities to expand this type of integrated study, which we see as fundamental to improving ice sheet reconstructions and GIA models. And the key here being collaboration and open communication. So I'd just like to close out by expressing my gratitude for the generous and lasting support for this type of work from the National Science Foundation, as well as Antarctica New Zealand, the Antarctic Science Platform, ANSTO and ANSI, the Australians that are supporting our cosmogenic measurements, as well as the Ohio State University, Te Harangawaka, Victoria University, Wellington, and Durham University. Thanks for your time.
Next up, we have Rob Bingham presenting Architecture Goes West towards an age depth model of the Western Arctic ice sheet from radio stratigraphy.
Well, morning stroke afternoon everyone. I'm Rob Bingham from the University of Edinburgh, and I'd like today to give you a quick update of the Antarchitecture project. Antarchitecture is a 4-year action group funded by the Scientific Committee for Antarctic Research, which is coordinating international efforts to use radiostratigraphic data collected across the Antarctic ice sheets, ultimately to try to produce an age depth model of the ice across the ice sheets. If I just play this video built from Joe McGregor and his colleagues in NASA doing the equivalent project in Greenland, you can still get a quick impression of what our concept is. It's to use the ice penetrating radar data that in our case have been gathered extensively across the Antarctic ice sheets, ultimately to try and get a spatially extrapolated impression of the age of the ice at any 3D position across the Antarctic ice sheets. So our motivations for this are various. They are to 3-dimensionally extrapolate the age depth information across the Antarctic ice sheets from the information we already have from ice cores. In doing so, we can then work towards reconstructing historical ice accumulation across the ice sheets. We can look for areas of elevated geothermal heat flux where the layers pinch out towards the bed of the ice. And we can potentially work towards reconstructing past ice dynamic variability. What of course makes this a significant challenge across Antarctica is that the data that we need to use are collected by multiple groups from multiple nations, using many different radar systems, and with traditions of processing the data in many different ways. And we also face a challenge ultimately at the user side, which is that at the moment there are a few numerical models that are actually yet developed to use the englacial data that we can gather from ice penetrating radar data. And I think that's a little bit circular because at the moment we actually haven't really developed a strong database analogous to things like BedMap 2 or BedMap 3 that's coming up, which can actually use the ice penetrating data effectively in ice sheet models. To address this across the international community and through the Scientific Committee for Antarctic Research, we formed a so-called action group about 3 years ago to try and assemble the available ice penetrating radar data and use that ultimately to work towards building an Antarctic-wide age depth model. And actually one of the main messages of this talk is that if you want to know more about this, please do contact me or join the Antarchitecture mailing list or look at our website, which will flash up on the screen a few times during this talk. Here in particular, I just wanted to give a little focus on our progress in West Antarctica, and actually through 3 developments. I'd like to talk to you about some age stratigraphies that have been developed over the Thwaites Glacier and across over to the Cycle Coast ice streams from our colleagues at the University of Texas. I'd like to give you an update on work that's been done in the Weddell Sea sector, some work led from Dave Ashmore and myself over in the UK. And then I'd like to give you an update on our most recent research on Pine Island Glacier, which has been led by my PhD student at Edinburgh, Julian Bodar. And just at the end, I'll give some conclusions and an outlook. Very quickly, just to flash it on your screen, I do want to give a nod to Martin Siegert, who actually began a lot of the type of work that we're talking about here, but only using the 1970s radar data. And you can read about some of those papers by following up with Martin or myself if you want to know more about some of the legacies that we're building on in this West Antarctic research. Here, though, I just want to start by summarising some of the progress made over recent years by our colleagues at the University of Texas using data collected over the Thwaites Glacier Saipol ice streams area. One of the key developments that's taken place over the progress of Gail Muldoon's PhD, which finished I think a couple of years ago now, was that Gail and colleagues, including Duncan Young and Don Blankenship at Texas, traced a number of layers widely over the Thwaites Glacier Saipol Coast regions. And in particular, they traced 4 layers which they traced also between the ice cores of Bird and WAIS Divide over a distance of about 160 kilometres. And from that, they actually got actually inferred ages of these 4 internal layers that track across quite a lot of the West Antarctic ice sheet. You can see here in the top left the spatial distribution of those 4 layers traced or dated, I suppose, to around 5,000 years ago, 9,000 years ago, 17,000 years ago and 25,000 years ago across the areas over which those layers could be traced through Thwaites and the Saipol Coast ice streams. And those layers essentially appear, this radargram here is from near the Bird ice core, so pretty much at the WAIS Divide. It shows that those 4 layers are distributed fairly equally throughout the ice depth, at least at the ice divide. And the main stories that we have of each of these layers so far are that the 4.7 thousand year old layer is easily tracked across most of the study region. It's actually drawn down to greater depths in the Thwaites Glacier region, as we might expect due to the enhanced ice flow there. The next layer that they traced at 8.7 thousand years was less widespread. They traced a 17.2 thousand year layer which links directly to what is probably well known to quite a few people in the audience, of the well-known supposed Old Faithful layer that is thought to be of volcanic eruption origin. And they traced a layer at 25,000 years old, admittedly over a fairly spatially restricted area. But to my knowledge, this is the deepest radar layer that's been traced over anywhere in the West Antarctic ice sheet. We'll now go to the Weddell Sea sector and the work led by David Ashmore. This has been published in Geophysical Research Letters last year, and in this work we traced 3 layers very widely across the Institute and Muller ice streams draining into the Filchner Ronne ice shelf. Of those layers, we were not able to tie directly to ice core data, and instead we assumed the ages from 1D modelling. But what we did find were 2 layers in particular. One of them, the middle layer traced in the Ashmore study, we believe to be the same layer traced widely across Thwaites and the Saipol region by Gail Muldoon, as discussed just before. And we also found another widely distributed layer across the Institute Muller at around 7,000 years old. That was a different layer to that which had been traced by Gail. We'll now move finally to Pine Island Glacier and the recent work led and published by Julian Bodar along with myself and colleagues. Julian looked at data collected by the British Antarctic Survey across Pine Island Glacier, but also linking it into internal layers that were imaged in Operation Icebridge, which allowed us to make a connection to the WAIS Divide ice core and put direct ages on these layers, which we could then link back into those measured across the Institute Muller ice stream by Dave Ashmore and co that I've just discussed. So in this project, we found 4 internal layers across Pine Island Glacier that we could trace over large areas. There are many more, of course. And as I've just said, we dated those by direct ties with WAIS Divide ice core. So I'll try and bring this all together now. The 3 upper layers in the Bodar et al. Study tracked across Pine Island Glacier. 2 of the middle ones are basically the same as the 2 lower layers in Ashmore's study traced across Institute Muller ice streams. And one of those is the same as the 4.7 thousand year old layer tracked across the Waits and Ross Divide. So a key message is that there is at least one internal layer that is very, very visible and very extensive across pretty much the whole of the West Antarctic ice sheet. The lowest layer that Julian traced was also one that was traced extensively across Thwaites and into the Ross sector by Gail Muldoon, and we think is equivalent to the Old Faithful layer that was linked to the volcanic layer in Bird Ice Core, and of course is visible in ground penetrating radar collected by Bob Jacobel and colleagues some years ago. I should say actually that the 3 of the layers Julian traced across Pine Island Glacier and linked to WAIS Divide ice core matched very clearly with sulfate peaks in WAIS Divide ice core, and that's something actually that was brought about in the review of that paper, and we'd like to thank TJ Fudge for some excellent comments that alerted us to that. And just a reminder that Gail Muldoon tracks that much older 25,000 year layer, the oldest one to my knowledge, across the WAIS Divide. Thank you very much for your attention. I'll just leave the conclusions on screen. So thank you for tolerating me going very, very slightly over time.
Next we have Terry Wilson, and can international consortia support pan-Antarctic observational networks?
Hi everyone, I'm Terry Wilson from Ohio State University. My goal today is to start a conversation about international support for observing networks in Antarctica. I'll remind you of recommendations in this regard from vision reports for future Antarctic science. I'll touch on a few frameworks that have been successful in the past in supporting international collaborations. And at the end, I'll encourage both agencies and the science community to consider some actions that might facilitate future interdisciplinary and internationally coordinated Arctic science, whether it relates to networks or not. So in 2011, the National Academy published the Future Science Opportunities in Antarctica and the Southern Ocean that outlined a very broad spectrum of compelling science that could be carried out in the coming couple of decades. One of the recommendations of many that they made was to lead the development of a large-scale interdisciplinary observing network that was linked with Earth system models. And they suggested the best way to move this forward was a coordinated long-term international effort. A second recommendation really aimed at NSF was to design and implement improved mechanisms for international collaboration, because they recognized that this could facilitate research that no single nation could complete on their own. In 2015, the National Academy published a strategic vision document that isolated more limited set of priority science from the broad spectrum identified in 2011. One of their recommendations was to lead a coordinated international Antarctic observing system network, and they also suggested that this should be done through a coordinated long-term international effort. The 2015 Strategic Vision Report justified their recommendation for this international collaboration by highlighting some very successful international collaborative programs in Antarctic science. So how were these funded? One model is represented by the androgeological drilling or the current International Thwaites Glacier collaboration, where several national polar funding agencies negotiate an agreement that each will contribute a certain proportion of the costs for the science and science infrastructure for a project, and science participation is allotted according to those proportions. And these kinds of projects generally last 5 years, perhaps up to 10. A longer term model comes from IODP, where a host of nations contributes funding to support the science infrastructure for ocean drilling. And again, staffing and science participation is proportional to the level of funding that each nation gives to this effort. The third model is represented by the Southern Ocean Observing System. This is a coordination model where national programs fund individual science projects, but those are brought together into a greater whole through coordination by an international project office that does planning and coordination activities. This is the only part of this model that has international funding. In the case of SEUS, this is by the Scientific Committee on Antarctic Research, on oceanic research, and various other national and international entities with interests in polar science. So when you think about successful international collaboration, of course, your mind turns to the International Polar Year, and of the many amazing projects that succeeded during IPY, we can point to the coordinated polar observations from the constellation of NASA satellites, the coordinated deployment of Argo floats for oceanic observations, the coordinated ground-based and airborne geophysical observations that allowed exploration of the subglacial Gamburtsen Mountains and the overlying ice sheet, the coordinated deployment of autonomous geophysical and geodetic sensors that really provided a step function in the spatial coverage of observing in Antarctica, Greenland, and other parts of the Arctic during IPY. I actually was the leader of this POLNet consortium for IPY, and I'm often asked, how does a project on this scale get developed? And so in a nutshell, we built a science community. That science community then established interdisciplinary science objectives and priorities. This was mainly carried out under the auspices of the SCAR research program on Antarctic neotectonics, which started around 1999. In the US, a group of scientists partnered with the IRIS Pascal and UNAVCO facilities to develop the technologies required to deploy autonomous systems in Antarctica with funding from the NSF MRI program that started around 2005. Meanwhile, community momentum for an international polar year was building, leading to the establishment of IPY committees. In the US, this was strongly supported by the national academies through their Polar Research Board, which produced a vision for science and related activities during IPY. And NSF made the decision to step forward and provide targeted funding for interdisciplinary and internationally coordinated science during IPY. In the case of observing systems, several projects that were supported to deploy autonomous systems. There are all the red symbols on the map on the right. So at the end of the IPY, we had successful autonomous systems technologies. We had in situ infrastructure. And I also want to highlight the ongoing legacy of open data, because that policy has not only allowed the science for the individual investigator groups, in our case, focused mainly on earth structure and solid earth deformation related to ice mass change, but also enabled science in completely different fields. For example, tectonics, ice sheet dynamics, atmospheric studies, ocean tides, geospace weather, with a cool upcoming example of using ionospheric total electron content derived from the GPS signal to study the December 2021 eclipse. So clearly more and more science is emerging from these data streams from this observational network, but will those network observations be able to continue? The footprint of the network is shrinking, and this is partly reprioritization of science objectives by the project PIs, and it's partly reduction in logistic scope of the project. And even with this reduction, this is still, in the current logistics environment, a challenging project to support. So we need a more sustainable model to continue observations. What kind of scenarios can we look at for the future? Well, let's look at an elimination scenario, which would take our observational capabilities as represented in this example by a solution from Ohio State, a vertical bedrock motion for all the GPS sites that continuously record in Antarctica. This is what our observational capability would be if we decommissioned the US ANET network, if we also decommissioned the UK ANET network. So clearly our current 3 to 4 year PI awards is not an optimal model to sustain these networks. So that brings us back to our question. Can one of these mechanisms that I've outlined for internationally supporting observing networks, are those feasible for the future support of observing in Antarctica? And I highlight here this new SCAR research program focus on the ice sheet and sea level because it provides a potential international science umbrella for thinking about the kind of network that I described or any other kinds of observational networks that this community might be interested in. So to wrap up, let's consider some of the lessons articulated in the National Academy report for the wrap-up of IPY. Directed to the agencies are these: more effective interagency coordination within and across nations, particularly in funding approval and logistics, would have been beneficial. And a formal mechanism for interaction of representatives of funding agencies from many nations and the international community-based planning committees would have been helpful. For the community, the report really emphasized that IPY was a grassroots effort. The research community was coordinated and rallied and established collaboration that made the IPY successful. So with that in mind, what observational networks does the WAIS community need and want to prioritize? This is really a call to action for the community to organize their thoughts on observing networks and priorities and communicate these to our funding agencies, but also to potential international partners. And I'll end by just reminding you that one avenue for this community to communicate about needs for geophysical and geodetic observations is through the Polar Science and Technology Committee, which is currently a joint committee of IRIS and UNAVCO, and presumably will be part of a future integrated geophysical facility. I've listed the current members here. The current leaders are Paul Wimbury and Matt Seifried, who are part of this workshop today. So please, let's turn our minds to this and take some action. Thank you.
For our final talk, we have Kirsty Tinto, the U.S. Antarctic Program Data Center, Data Archive, and Project Catalog for Antarctic Sciences.
Thank you. Hi, you've seen me before. I'm Kirsty Tinto, and at the moment I'm speaking on behalf of the USAP DC, the data center that is funded by the NSF, and it's an archive and a catalog for all of the data that we're generating in the projects that we've been talking about during this week. So first of all, who we are a small team. There are 4 of us. We're based at the Lamont-Doherty Earth Observatory at Columbia. Suzanne Carbot is the main PI. She's a marine geophysicist and she's involved in a lot of data repositories across different disciplines. Frank and I are the day-to-day people at the end of the email. If you email info@USAP-DC, you're going to get a reply from one of the 2 of us. We're polar scientists and interact with the science and the data science communities. And then Neville is our programmer who builds the infrastructure and makes everything work. So that's who we are. But what we do is support data discoverability and archive to make sure that our science results endure and can be used generationally beyond the people who are generating the data at the moment. NSF knows that this is important, and so there are obligations that come with your awards to make sure that data are safe and shared and available, and that's why we are funded to help you to do that and be the place that the data can come to. So we're supporting your obligations, we're preserving the unique observations that we make. I've got a couple of pictures of lovely blue sky days in the field where loads of data come in. I also have pictures saying, remember, not all the days were like that. These were really hard data to win, and you don't want to lose them. And also to comment that not all important data contributions are field-based, that we also take derived products, models, anything that is the product of a polar award, an Antarctic award, can have a home at USAP DC. And you never know where those data are going to be useful beyond the scope of your own project, as we've heard in the talks that preceded me. So this is really the slide that you should see and recognize. This is how you find USAP DC. This is what the homepage looks like. And the major functions of what we do are in big buttons in the middle of the page. So we're pretty easy to interact with. But we're here to support the full life cycle of data in the science process. There's a lot of early career people here, so you might not yet have written your first proposal. You're going to love it. One of the things that you need to do is to include a data management plan in the proposal. This shows that you've thought about what measurements or what data you're going to produce, how big it's going to be, where you're going to put it, how you're going to distribute it. And we can help with that. On the site, you can navigate to this easy DMP tool. It gives a template to ask you the kind of questions that you should have answers to if you're going to be completing data. You log into the whole site with your ORCID researcher ID, and that will keep a template of the old data management plans that you've submitted in the past. So next time you write a proposal with the same sort of data formats, most of your work's been done for you by earlier you. So that's a really handy thing. But of course, that proposal is going to be awarded. And when it is, you're going to be really excited, and you're going to get the award letter from NSF, but then you'll also shortly get an email from USAP DC. A bunch of people might have got them in the last few months, welcoming you to the data center and letting you know what you can do to start getting involved in it immediately. Because within the first year of your project, we encourage you to register at USAP DC, and we'll create a project page. So it's like a home page on the data center website that describes your project. You'll hit the big register project button to do that. You'll be stepped through a web form, most of which is pre-populated because you've already written all this in your proposal, but we'll move it over and we'll make a website for you. And the nice thing about it at the bottom here is there's an edit button at the top of the page. So this project page is going to live through the life of your research project. And you'll add to it, you'll add data sets, you'll add publications. It'll grow, but it'll pull all the different contributions from your project into one place. And that's extremely helpful for other people finding what you've done. So the project page will look a little bit like this. It's just got fundamental information about the award. You make it before you've even got any data, so it's really easy to do. But you can see at the bottom there that it will list all the different data sets that end up being attached to the award. And it doesn't matter if they're archived with us or in another repository. You can see on the left of the table, maybe you can see, other repositories will link in and everything will still be pulled together on the one page. To explain that a little bit more, once you have data, and the rules are that this is within 2 years of collecting the data or before the end of the award, whichever happens to be the shorter, you should submit the data somewhere safe to a permanent archive. We are one such place, but as I say, if your discipline has another archive that is where the global community are going to look for your data, not just polar, then you're absolutely welcome to submit your data there. And then we can link in to external data centers if that makes more sense. But if you lodge data with us, it's the same, stepping through a web form that asks everything that we need from the data, fundamental metadata like where and when, what units, things like that, and then anything else that you can include that would help somebody use those data go into the README that you'll make. We assign a DOI for you. This data set will be citable. It will get its own page like this that gathers together all of those data. It links back out to the project that you were funded from that got the data. It can link back out to more than one project if there were collaborations that brought it together. And there's a button at the bottom that allows you to download that data set. This is for internal USAP DC data holdings, and for the externals, you'll be sent somewhere else. There are some thresholds of data volumes of what can actually be directly downloaded, but it is all available. And if there's anything that you can't get by hitting the button, then just email us and we can make it available to you. At the end of the project, your obligation is that the project is registered with the Antarctic Master Database, but you've already done that, because by registering with us, we prepare that. We give you a presence at the Master Database. So that is lifting some of the admin burden from you and your data. It also makes your data set available to all Antarctic workers and everybody in the world, really. The master database is fed into by all the different nations who are conducting work in Antarctica, and that is the central area where you can link those two. We also link the data out to Data One, and it's available through all sorts of different search tools. So we'll have done your IMD record. Publications that refer to your award will be automatically added to your page. You can add them yourself if you want to with the edit button, but we go through and find them if in Crossref if you've got the award acknowledged, and so you will find your page growing and all the contributions from different collaborators showing up over time, which is kind of cool. And then in the last part of this data cycle, but obviously it's often the first part of the work that you want to do, there is the data search facility. So we are making your data visible so that it can be as useful as it can possibly be. And we're also a resource that you can dive into and find what data exist. Who's already been where I need to go and get some answers? Where are there no answers and I need to start writing a new proposal? It's all in the search facility, which again, press one of the big buttons on the page. We've got different ways of searching for data here. It can be text-based, it can be location-based. This is a way of filtering through the different programs that fund projects, and you can search for specific regions or overlay different data sets to work out exactly what you're looking for. But I'll go back to that really, really important page. We are the USAP2C. We're here to make your data life easier. And if you have questions specific to your own data sets, then I'm here today and at the end of the email, so please do go ahead and ask them. And that's what I have to say.
Wonderful. If we could have all the in-person presenters come up. Okay, we have one online question from Terry, if you want to ask that.
Yeah, hi, this is for Louise, and I was wondering if you had thoughts on actually constraining the orientation of the tectonic structures and basins you're inferring, because with your current single line down the axis, of course, you don't really know their geometry.
Yeah. Is that working? Yeah. Yeah. I didn't really show a map of the features, the topography of the weights in a map view, but we're kind of looking at features that are running roughly orthogonal to the direction of ice flow. So I guess our original thought was that these basin features would also run orthogonal to the ice flow and be fairly continuous, but when we're looking at that gravity signal, it looks like there is some 3D effects going on, so these are potentially not so continuous all the way across orthogonal to ice flow as we thought. So yeah, we're going to be looking into that further and the exact kind of geometry of the features, not just in that 2D line that I showed.
Yeah, I think it's important. Do not trust topography for orientation of structures. That's been proven over and over again in Antarctica from bedrock. So yeah, well, interested to see what you come up with. Thanks.
Thank you for the talks. Kirsty, I have a question. Is there any way that they're ensuring that the data is accessible and uploaded properly on this website? Like, is there any kind of process being done to ensure that it's accessible? And if it isn't accessible, does that taken up with the individual scientist or?
Yeah, good question. I love to talk metadata. We make sure that the fundamentals are there in the web form, and then when you submit anything to the data center, either Frank or I will put eyes on it and go through and check that everything that we really need to have is there. There's an additional check that will go in when we make the AMD entry for you to make sure that the standards are there. But there might be things specific to your discipline that we don't necessarily know is critical, so we do a lot of trusting you to be as good a citizen as possible. But we'll just email you back and say, hey, what is column 3? Mm-hmm. And it's a pretty easy fix.
And I have a quick follow-up. If the data, I saw that if it was larger than a gigabyte, you have to contact for access. Is that something that you all get back to, or is that the individual researcher as well?
So if you submit a large data set, there's just a limit on what goes through the web form because the system will hang and it will annoy you. Mm-hmm. So it's easier to send that a different way to us, and we'll work out that way just by email. Okay. And then for downloads, again, just for the giant ones, so everything's stored on the cloud so that the giant data sets aren't being downloaded constantly. If you request it, we'll put it in another place and you can FTP it, and then we'll take it back down once you've got it safely.
Thank you.
Thank you all again. And Kirsty, I had another quick question, and I apologize if I missed this, but is the USAP DC just for NSF-funded projects, or can anyone submit to it?
It's for US and NSF-funded work. There are other archives that usually exist for other programs, like NSIDC is taking a lot of NASA data. But if there is a project that a US researcher has a particular interest in, like, is involved in and thinks that this is the right home, then we can talk about it. But it's predominantly, you'll get the award letters because we organize the database on NSF award number. So everybody with an NSF award will definitely hear from us, and other people can reach out if there seems to be a need.
Great talks, everyone. Thank you. I had a couple questions. One of them was for Kirsty, but I think since you've had a few questions, maybe I'll go for one of the others. Yeah, Louise, and this is something that maybe others could speak to as well. We've seen, for logistical reasons, a lot of the projects at Thwaites get delayed, unfortunately, and in particular, GHOST has gotten pushed back a lot. Ideally, that project would have brought in information on basal properties as the modelers were kind of doing their thing and incorporating those data into the models. How do you see, as you're starting to look at some of the seismic data that have already been collected and then that data that will be collected with the GHOST project, how do you see extrapolating those data over the Thwaites catchment, and then what kind of future modeling questions do you think are the next step after we have those data to incorporate? That might be a big question, but if you have anything to speak to, that would be awesome.
Yeah, for extrapolating over the whole catchment, the airborne data is going to be really useful, just because obviously you can't cover much distance with seismic. And obviously we already have most of that, so that's really good. But we just need a little bit more. The seismic data gives us really good constraints on especially these upper crustal features that, like with the non-uniqueness of gravity and magnetic data, we're not quite so sure on the constraints of the sedimentary basin. So I think we just need a bit more seismic data to really help constrain these features better. And then it will give us more confidence with what we're seeing in the airborne data. And the second part of your question was about with the models.
Yeah, I guess just the modeling questions that we've seen being addressed so far are a lot to do with kind of the ice-ocean interface, and then we saw this talk from Alex today where he's starting to incorporate some specularity data into some of the modeling that he's doing. I'm curious what your perspective is on how the seismic data will kind of progress some of the modeling into the future.
Yeah, so I guess it really will help with how we're modeling how the ice is moving at the bed of the glacier and the basal shear stress. So yeah, I guess with how that's incorporated into models, and I guess part of the difficulty is what we're seeing is potentially variable basal shear stress, which is also difficult to incorporate into models. So that could be an additional challenge if that's what we kind of find as a result.
Thank you.
I wanted to jump in before the next question. Sorry, Kaya. To say that the part of the project that we're working in together is figuring out how to get regional extents and put them usefully into models just by starting with the zones that you can define from the geophysical properties and working out the kinks of those integrations. And Louise's work of shining the light of seismic truth on those zones is a really crucial part of what we're doing.
Thank you all. That was a really exciting session. I feel like we hit some fundamental work about how does this system work. I'd be curious to hear from all of you what in your small corner of the field is the roadblock on the next huge advances. Is it battery technology? Is it funding? Is it human power? Is it really observations? I think we keep stressing we need more observations, but what's your perspective on what are the major roadblocks keeping us from the next huge discovery?
I guess I go the furthest back in time, so I'll start. I think for the paleo community, one of our biggest challenges is access to samples. And in my case, I want to drill a bunch of holes into the ice sheet. So getting the funds and technology to do that efficiently and as cheaply as possible so that we can do it more, I think is a big challenge. But I also think that there is an additional challenge of the perception of paleo data and the value it plays in our interpretations. I think that we as a community need to do a better job interfacing paleo observations, modern observations, and models, and just kind of learning how to communicate between our kind of corners of this scientific world is one of the big challenges we need to overcome.
Yeah, I also have a comment in that regard, if I may.
Yep,
yes?
Go ahead.
Okay. Yeah, I mean, right now, for everyone's vision of future work, logistics is a challenge, but I'd rather not focus on that, but ways that we might spread the logistic burden to make it more feasible. And one of those is international coordination, which I emphasized in my own talk. I think more countries putting resources into the kitty will help that situation. But I also think very important for NSF, for us as a US community, for NSF to have more clear and transparent mechanisms to build these international collaborations so that they can be supported. Another avenue is, of course, technology. If we can improve the technology so that, for example, in situ systems like are in the ANET POLNet network can run for years without needing science maintenance visits, then obviously that's going to ease the logistic burden. So there's a lot of pieces to the puzzle. And I think some kind of focus on moving all these pieces forward will help build the framework for new discoveries as we go forward.
Yeah, I guess following on from that with geophysical measurements, it's never ending. You could cover the whole glacier in seismic measurements, that'd be great, but that's not going to happen. So, yeah, more seismic measurements would be great, basically.
And I think that the points that have gone before are really crucial, the timescales and the nations. But honestly, if you just ask me in my cold heart what I want more rocks from underneath the thing. So I'm excited to have a seismic line that interprets a whole field of aerogravity area and just a couple of little holes in their ground that will show me what the rocks are. I really want to see that, and at the moment I have to trust the ice sheet to have spat them out thousands of years ago, and that's just a harder job.
So my first question is for Ryan, actually. I really enjoyed that talk. I didn't know you could get ages or that kind of context from that setting, but I was wondering what exactly the newer sources of those younger ages are. And is it just, like, can you tell it's marine? And I'm also wondering if it's possible that seawater going under grounded ice could carry that material to those sites.
Thank you so much for asking this question. If my talk were 50 minutes long, I think I probably would have touched on all of those things. So something I guess I didn't get to is that subglacial lake systems are incredibly easy because they're covered by an ice sheet. So there's no exchange with the atmosphere that could bring radiocarbon into the system, and it makes it so that there's only one door. And the only door is that the grounding line has retreated past this system and enabled basically marine water to bathe the sedimentary basin that's there already. We're too far from the modern grounding line for kind of, I think you're making reference to some of the processes that Alex Roble talked about a few days ago, yeah. So we're a little bit too far at the site that I worked at for that to happen. And we know, because we measured all of the other parts of the subglacial system to really characterize the whole subglacial carbon cycle, that there are no upstream sources of radiocarbon. So really the only option is either that something was blown in from the ocean, but we're too far away from the ice front for it to be something particulate, or the little critters that are living there, being amphipods and fish, are pooping all over the place and dropping their carbon. But you're a geologist, you know that those things are preserved. We don't see anything like that. So the last option, which really jives with the stable carbon isotope measurements, is that there was carbon fixation by microbial organisms that were living on the substrate. And this explanation jives really well with how much young carbon we find. Only about 3% of the total carbon pool in these sediments is made up of the young stuff. And that fits really well with rates of microbial fixation that would have enabled the deposition of a pool that size within a short exposure to the marine environment. So I'm talking like hundreds of years, so not very long. Hopefully that really long explanation answers your question.
I have a question also for Jamey. And it's technical. I know we did a lot of big picture questions, but I'm going to bother you guys about technical things. So part of West Antarctica is uplifting really fast. Is that also associated with a forebulge collapse of any kind, and how far away is that from that uplift, if you know?
Yeah, I'm not sure. I mean, I think the sites that I mentioned were a bit far away from, were kind of periphery to the main kind of ice mass changes that we see around Thwaites. Most of that signal is dominated by more modern and more recent ice mass changes. Yeah, sorry, I'm not really sure. Maybe Terry's got some more thoughts on that.
No, that's fine, thank you.
We have another online question for Jamey while you're up. The question is, how do you separate out the signals from changing surface mass balance versus GIA in terms of how the bedrock is exposed at the surface?
Yeah, I'm just trying to get to that now. I've been thinking on it there for a minute. I'm not exactly sure I understand the question. You know, basically what we tried to outline was the kind of ability to separate the two signals, the more elastic response that's related to the more modern mass changes versus the GIA, which is the more kind of centennial to millennial scale. But in terms of how the bedrock is exposed at the surface, yeah, I'm not really sure. I mean, possibly the subglacial exposure ages may help that. But yeah, Richard Jones wrote a really great paper on the impact of GIA on exposure ages. I think it was in 2019. And I might look to that for a bit more detail on, yeah.
Hey Ryan, I had a quick question for you. So you mentioned you want to drill holes all over Antarctica. Is there a specific region or maybe a specific lake that you think should be a top priority for the next big drilling effort to get down to subglacial lakes?
South Pole Lake. But to kind of expand on that, I think we need to go inland. So we've been in the 100 to 150 kilometers away from the modern grounding line range, and I want to know how far the grounding line retreated in the Holocene, and we're not going to know without poking more holes. So.
Hi, thanks for an awesome session. I have a question for, I guess, sort of Terry and Kirsty, and then anyone else who has thoughts. But it seems like in the next 5 years or so, projects like Starlink may allow for like increased internet connectivity in polar research areas. And so I'm curious if you have any thoughts on how that might sort of change the landscape of data services with potentially increased data volumes, and also how that might change the landscape of proposals and project design.
Well, certainly for in situ remote autonomous instruments, having more bandwidth for data transfer would be very important. At the moment, we can transfer all the GPS data through the existing Iridium connection, but for the seismic data, that is not the case. So to cut down on the need for site visits, to have the bandwidth to transfer data would allow more science with a lower logistic footprint, which is really the goal right now. So I think it is an important advance we should be looking at.
Thanks.
And I can say that in terms of proposals and the sort of science that we'll be thinking about, it feeds into that open science idea that's so transformative that you can lose the lag time of how long it takes to recover data and to get them processed and out into the world. So we can be thinking more about active collaborations as the data are coming in, and finding those ways of translating our data products for each other, which I think is going to be a really important step.
Thank you, I appreciate it.
Can I comment on this? Because there's an
important point here, and I would like to ask Kaya Riverman what it was like digging out a station on Pine Island Glacier. Miserable. So, like, these technology improvements are great, but there's a fundamental issue still. If we want on-ice data, we still need boots on the ground. And so we can't forget that, you know, we can put long-term instrumentation on rocks that aren't accumulating snow a lot easier than some of the places we need to get to. You know, an instrument in a shear margin is not going to last forever. And so Starlink is great, and it's going to make some improvements, and we can eke out some %, but it's not a panacea. And it's the same with the subsea cable, Peter. Ted want to know if I want to make robots that can climb out of the snow, and I do, but this is why we need engineers in the room. And so Dusty's group is doing a great job of bringing engineers, and Brent's group, but I think we need more. Like, drones aren't going to save us either. And we need to expand our community, and we say on the WAIS Workshop website, we want engineers here. So bring your favorite engineers. You know, I've spent 10 years of my life digging GPS out. And I talked to UNAVCO about new designs and stuff, and we need to think about these kind of old school techniques while we talk about the new techniques as well.
Hi, I just have a quick question for Ryan. Really cool talk. I actually missed the very beginning, so I'm sorry if I'm not understanding something correctly, but you mentioned that the stable carbon isotopes indicated carbon fixation, which I assume is under the ice. And so I'm curious if that's autotrophic activity, what is their chemical energy source, and then as an alternative, I'm just curious whether it's possible for photoautotrophs at the surface of the ice sheet to kind of drain down and end up under the ice.
I can't believe I'm sitting at WAIS Workshop and someone just asked me about chemoautotrophy. This is the best day of my life. So we think we've identified like a two-step process. So there are modern biological communities being observed by my collaborators at University of Florida. And basically the DNA data that they're generating indicate that Kelvin-Benson fixation is the primary fixation, so CO2 in the dissolved form in the water. And then I also did some compound-specific stable isotope work, and we identified a lot of butyl esters in the sediment, which could be associated with basically lipid production. So in terms of like where the carbon is coming from, it's being fixed from the water column and then deposited as kind of like organic goo, essentially, for people in the room who don't speak our language. And then we observe no evidence for kind of like this percolation in Antarctica today, in this area, and it's not likely that it was that way during the Holocene either, but that would be really cool. That would definitely be the case somewhere like Greenland.
Thanks.
Awesome. Let's thank everyone for this session. And before Matt comes up, let's thank our conveners for a shockingly good hybrid meeting.